Great. Let me see if I can start my video. Okay. Hopefully I have enough bandwidth for this. We'll see if it works. And then we start sharing the screen. All right.
Okay, great.
Let's see. Okay, yeah. So thanks for the invitation to speak at this next workshop. Nice to have everybody together to talk about these topics, which I think are really exciting. Today I'm going to talk about many-body electric multipole insulators, and I'm going to focus on two different aspects. One aspect is going to be on the calculation of electric multipole moments in many-body systems. And the second aspect will be on field theory representations of their electromagnetic responses. So let me start by thanking my collaborators. So Easy, Fiona, you all know, I have two really strong students, Oleg and Julian, who have participated in a large portion of this work. And then I have two other collaborators, Will Wheeler, who's a grad student at Illinois, and Lucas Wagner, who's a faculty member at Illinois on some parts of the projects. So let me begin. So let's first review how you calculate the electric polarization in many-body systems. So many-body ground state, suppose you're in one dimension, the typical formula for a single particle system is that you calculate the Zach phase or the Berry phase integrated around the Brillouin zone. But for a many-body system, there's no Brillouin zone, and so you create one by threading flux, and you integrate over the space of twisted band conditions, and you can calculate the polarization to this integral. About 5 years later, there was a second method proposed by Resta, where you introduce this many-body unitary position operator or a many-body twist operator, and then you with this many-body operator on the ground state. And what you find is that any gapped ground state is almost an eigenstate of this operator in the thermodynamic limit. And the eigenvalue is related to the polarization through this unitary phase. And so Resta proposed that you could take the expectation value of this operator in a ground state, and then take the imaginary part of the log of this expectation value to extract that polarization phase. And in the thermodynamic limit, you would recover the charge polarization. So for the quadrupole moment, the situation is a bit more involved. So first of all, there's not an obvious way actually to do the Berry phase at first. And I'll show a way later to come back to do this twisted band condition idea, but at first there's no obvious way to do the Berry phase. One can introduce a many-body quadrupole twist operator, analogously to what was done before. And you can follow the prescription that Resta used, for example, and define this many-body expectation value and take the log. And we calculated this structure, this quantity for, let's say, tight binding models, and you can show that it matches. You can show that the quadrupole moment matches the difference between the corner charge and the edge polarizations, which is the typical extraction for the quadrupole moment. But there's a subtlety, which is that this works in finite size, but it turns out there's an issue. So typically in the thermodynamic limit, this calculation for the polarization is well defined in the thermodynamic limit, because the magnitude of this expectation value z sub x goes to 1. So basically, as I said, the ground states become eigenstates of this operator in the thermodynamic limit. It turns out for the quadrupole operator in the thermodynamic limit, the magnitude of this operator goes to 0 for these tight binding models. And that means that you can't extract the phase in a meaningful way as you use larger and larger system sizes. So basically the idea is that, if you have finite size effects in numerics, you would gradually increase the system size, and eventually the magnitude of your expectation value would be 0 to machine precision, and you would lose any ability to calculate the value. So this is a sort of confusing point for tight binding models, which I'll come back to in a minute. So let's talk about the magnitude of this polarization expectation value and see how it approaches 1 in the thermodynamic limit. And it turns out the way it approaches 1 has a physical interpretation. So it turns out that you can take the log of the magnitude and multiply by some factors, and this determines what's called the charge localization length. It tells you something, for tight binding models, it tells you something about the sort of minimal width of maximally localized Wannier functions, but it basically tells you sort of how much the charge is localized in the system. And it turns out that in thermodynamic limit, this value goes to in thermodynamic limit, for insulators, this charge localization length tends to 0, for example, in the thermodynamic limit. So there was a beautiful work by Resta and then by Richard Martin's group, which later shows that this charge localization length is actually related to the fluctuations of the dipole moment, right? The polarization is like the average dipole moment of the system, and this charge localization length is like the amount of fluctuating dipole moment. It's like gives you the first moment of the distribution of the dipole moment for that physical ground state. And it turns out that this dipole fluctuations is exactly related to this correction, which goes to 0 in the thermodynamic limit. So there's a nice paper, again, by Resta Sorella, Legia Ortiz, and by Susan Wilkins Martin, which used this idea of charge localization to propose a many-body definition for metals and insulators, which can work just given a ground state. You don't have to know anything about the excitation spectrum. You don't have to know anything about the behavior with twisted boundary conditions. And what happens in the thermodynamic limit is that you have a metal if the charge localization length becomes infinity or diverges, and it's an insulator if the charge localization length goes to a constant. So the issue we see here is that this idea actually leads us to the problem with this quadrupole operator, which says that even if the dipole moment vanishes on average, it turns out the distribution of dipole moments is not 0. There can be fluctuations, for example, and this causes problems with the calculation of the quadrupole moment because the quadrupole moment is only uniquely defined if the system is neutral and if the dipole moment is exactly 0. And it turns out that being 0 on average is not good enough to use this operator, at least in the thermodynamic limit. So what we want to study, if we want to use this operator to calculate the quadrupole moment, we want to study systems where this dipole fluctuations are exactly 0, where there's no charge fluctuations. And for free fermion systems, this is very restrictive because it means that the Wannier functions of your insulator must be exact delta functions that have to be localized on a single site. So for example, many of you are familiar with the SSH chain where you can have this strongly dimerized limit where the electrons are sit on 2 sites. It turns out that's too big. That doesn't even work. To use this operator, you have a finite charge fluctuation length. And so this is really too restrictive if we want to study free fermion systems. But it turns out if you want the charge localization length to be 0, you can study many-body systems, and you just need to have it be 0, you need charge conservation and dipole conservation. This will set this charge fluctuation length to 0. So just as a review, charge U1 global charge symmetry means you can rotate the phase of your charged operators. And that means that as long as you have as many daggers as undaggers in your Hamiltonian, you will have charge conservation. Dipole conservation means you can rotate the operators by a phase which is linearly proportional to their position. It's not an arbitrary function of position, but it's a linear function of position. And it turns out that the types of operators which can preserve this, if you actually want motion off-site, have to be quartic. And so one example is this ring exchange term, where you have either a pair of electrons hopping, you have a pair hopping term which preserves the dipole moment. This can conserve this dipole symmetry. Okay. So we want to study, if we want to use this many-body quadrupole operator, or systems which have this type of dipole symmetry. So one consequence of having this dipole symmetry is that now your ground states are gapped, and now your gap ground states are exact eigenstates of these twist operators. So whereas before they were only approximate eigenstates in the thermodynamic limit, now they're actually exact eigenstates because they have a fixed polarization, it doesn't fluctuate. And that also means you can couple the system to a rank 2 gauge field. And so in this case, you have a new type of chiral phase factor, which couples the ring exchange terms. And so it allows you to add a phase factor to ring exchange terms. And if you broke the dipole symmetry back down to just U1 charge conservation symmetry, heuristically, this gauge field would just get replaced by the gradient of the regular electromagnetic field. So you can think about this rank 2 gauge field in this context as being something like the gradient of the typical electromagnetic field. And that's meaningful because that the actual, dipoles don't couple to electric fields. They only couple to sort of, dipoles in this case would only see the sort of gradient of the electric field if they're going to couple in this case. So now we can use these ideas that were developed for typical metals and insulators by generalizing this idea to dipole conserving systems. So first of all, we can generalize Cohn's criterion for insulators, which is that the ground state is insensitive to twisted boundary conditions. And instead of twisting a normal gauge field, we're going to twist this rank 2 gauge field. And so you can show that you can define a dipole stiffness, which characterizes whether the system is a dipole metal or insulator, by seeing how much the ground state energy changes as you twist this rank 2 gauge field, basically as you twist these generalized chiral phase factors. You can also define a dipole localization length. So remember, the charge localization length is 0. You can now define a dipole localization area, not length, related to the magnitude of this quadrupole expectation value. And you can use this idea to relate the quadrupole fluctuations to this dipole localization area. And based on this, we were able to define a criterion which determines whether a charge insulator, which conserves dipoles, is now a dipole metal or a dipole insulator. And it depends on whether this dipole localization area is either finite or infinite in the thermodynamic limit. And so this allows us to refine the idea of charge insulators if you have conserved multipole moments into breaking them up into things like dipole metal or dipole insulator. And if your dipole insulator conserves quadrupoles, you can have a quadrupole metal or quadrupole insulator and so forth. And so this gives you a way to now think about this sort of hierarchy of conducting or insulating these different multipole moments. So let me go back now to the Berry phase prescription. So with this setup, we can now talk about the Berry phase idea. So now remember our ground states are exact eigenstates of these many-body position operators. And we want to pick a case, if we want to talk about quadrupole moment, we need to pick a case where the polarization is 0. And so I want these states to be exact eigenstates with eigenvalue 1, for example. So the polarization vanishes, the phase vanishes. And now I can think about the quadrupole moment acting on the ground state as giving me some phase up to the quadrupole fluctuations that vanish as 1 over L. And so what you can do now is you can think about twisting boundary conditions by twisting this rank 2 gauge field, for example. And you can define a Berry phase by looking at how the ground state changes with this shift of the rank 2 Berry phase. And you can calculate the quadrupole moment by looking at the integral of this twisted boundary condition space in this case. And so we can show how this works with a simple model. So we're going to show this model, for example, which has intra and intercell ring exchange determined by T, which is the intracell ring exchange, it's like a pair hopping, and lambda, which is the other quartic ring exchange term. So these are 2 quartic terms. And we can tune the system so that either T equals 0 or lambda equals 0. So it can be exactly solvable in those simple limits. It's just a cluster limit. And we can calculate whether these things are dipole metals or insulators by using our criterion, and whether they have a quadrupole moment or not using our Berry phase calculation. So if we let T equal 0, the system now has this intercell ring exchange. It's like kind of like an SSH chain generalized to ring exchange in 2D. The ground state is a product of all these product ground states, each cluster. And you can calculate the dipole localization area. And you can show that it's finite, equal to the lattice constant squared over 2, in even the thermodynamic limits. The system by criteria, when lambda is finite and T is 0, is a dipole insulator. So now we can ask if this dipole insulator is a quadrupole moment. We do this by tuning the phase on each plaquette, this sort of Pyros factor. And you can show that if you calculate this rank 2 Berry phase, you get exactly pi. And so the system has exactly a 1/2 quadrupole, which you can confirm by actually calculating things like the edge polarization, which is 0 in this case, and the corner charge. Okay, so we have this idea now of these types of dipole metals and insulators. I want to briefly talk about a kind of field theory description. So for the 1D charge insulator, you can represent its polarization as just the polarization coupled to the electric field. For the rank 2 case, it's just going to have the quadrupole moment coupled to the rank 2 electric field. So we can now have this rank 2 electric field. This is a 2 + 1 dimensional field theory. It's like a theta term version of this 1 + 1D field theory. And if you calculate the response, you find the charge density is equal to the double derivative of theta, and the dipole current is the time derivative of theta. And these represent the exact equations you'd have if theta over 2 pi is the many-body quadrupole moment in this case. And so in this case, you can also, for example, take the dipole symmetry and break it just down to U1 charge conservation symmetry, which will replace EXY by these gradient fields. And then this will give you, instead of a dipole conserving insulator, will give you just a 2-dimensional higher order topological insulator with hopping terms, basically, or related to hopping terms. And this just shows you the quadrupole moment couples to the gradiented electric field, as you'd expect from just ordinary E&M. So we can now take this idea one step further, which last thing I say before I wrap up here. We know that if I have a Chern insulator, you can thread flux, and we have this Chern-Simons response. You can dimensionally reduce that, and now what happens is when you thread flux, you'll get charge buildup on the ends, and if you fix the amount of flux threaded, this exactly gives you a polarized 1D insulator when the radius of this cylinder goes to 0. And basically this means you can compactify the system and keep only one of the vector potentials, for example, and you get this theta action. Right? So now we have a theta action for the 2-dimensional dipole insulator, which tells us about a quadrupole moment, and now we can ask, is there a related Chern-Simons term that dimensionally reduces to this? And it turns out there is. And this Chern-Simons term represents a system which is anisotropic, which has chiral hinge states on hinges parallel to the z direction, and has other states, for example, organic surfaces, for example, or at least they have a charge gap, for example, on the surfaces. So you can think about this type of rank 2 Chern-Simons theory as being an analog of the typical Chern-Simons theory, at least in this case. And it gives you an anisotropic theory, which represents a 3D chiral hinge insulator with conserved dipole moments. Right? And so this theory is a bit strange because it turns out that it's gauge invariant in the bulk and on the surface, but not on the hinges, which represents this sort of hinge anomaly. But the funny thing is actually this configuration, which is gauge invariant, actually reduces to a boundary term. And so it turns out that this theory, despite having this sort of bulk form, doesn't give you a bulk response. It basically tells you that you get hinge currents in this case. You get this sort of hinge anomaly. And you can think about the response in these different ways. This type of Chern-Simons theory, as I mentioned, if you spread flux, you get charge buildup on the boundaries because of the typical chiral anomaly structure. If you put in a rank 2 gauge field, which is like a gradient of electric field, you'll get a hinge current in the z direction. And if you put on a normal electric field, you get a dipole Hall effect. So basically on the surface, you will get a current which moves both perpendicular to the electric field and moves perpendicular to whatever the dipole moment is of those dipoles on that surface. So it's almost like a spin Hall effect type of thing where you get this type of thing, but it's for dipoles instead of spins. And so there's a vector charged version of this theory, which you could ask about if you're interested, because I'm running out of time. And there's sort of a couple natural places where this will appear. So I'll just leave this on the screen and then stop here since I'm out of time.
Okay, thanks, Taylor, for the nice talk. Dominic, you have a question?